All right, so we just saw in our buffer problem that the amount of acid and conjugate base, which is common ion, are large compared to the amount of the H plus or the OH that is added, which we literally can see that right here. The HA, the acid, and the A minus, the base, are much larger than the OH minus that was added. So the pH barely changed. We went from a 4.74 to a 4.77. Okay? Now we did a lot of work to get there, but we can rearrange our Ka, because our Ka starts off with H plus times A minus over HA. So if we rearrange that to get H plus by itself, we get, and I will rewrite this so that it's got a much more pronounced fraction. HA is Ka times HA over A minus. Okay? So notice that HA is the acid and A minus is the conjugate base or common ion. If we take the log of both sides, we get pH equals pKa, because separate that out. Okay, so pH equals pKa times the log of the base over the acid. So when we take the log of that, that switches. So I'm going to rewrite this again so that we can see the fractions better. So of course pKa, negative log of the Ka. Okay, and then this is the log of the concentration of A minus, which is the base, over HA, excuse me, which is the acid. Okay? And so those concentrations can be just the buffer, therefore before adding acid or base. So in that problem we just did, before the pH equaled the pKa, because A minus and HA were the same. So I'm going to go back up to that. So look right there. See how the H plus, right here where the check is, the H plus ended up equaling the Ka. So pH equals pKa. And then if we do it after adding the base, our pH would be the P of 1.A. Well, I already know that the pKa is 4.74 because we did that. Okay? Plus the log of the concentration of the base, which is 0.51, over the acid, which is 0.49. And calculator. So, whoops. Divided by 0.49, and then take the log of it, and 4.74 minus 0.01737. Something's not right about that. Let me go back and look. Okay. We should go up to 4.77. So I've got my base over, whoops, wrong button. Okay. Put the whole thing in the calculator at once. Don't try to do it part by part. Because look, when I put in 4.74 plus log of 0.51 over 0.49, I get 4.76, which, doing it the other way, we got 4.77. That's just a rounding issue somewhere along the way. Or, as you can see in the previous line on the calculator, I literally put in pKa plus the log of the acid over the base. Okay? So, the Henderson Hasselbach ends up making a buffer problem a whole lot simpler. And you can even do the stoichiometry in it. Okay? So, here's our, whoops, stop writing in highlighter. All right, so here is our Henderson Hasselbach. Okay, so if we add moles of a base, you add to the base, you subtract from the acid. You add moles of acid, well, you subtract from the base and add to the acid. Okay, so keep scrolling over here. So let's say we added the O2 moles of HCl to 1 liter of the buffer. Well, we could go back and at this stoichiometry step, we could do like we did there, but adding an acid instead of a base. But because of the Henderson-Hasselbach equation, we only have to do pH equals negative log of 1.8 times 10 to the minus 5 plus log of 0.5 minus 0.02, 0.5 plus 0.02. Okay, and our calculator will handle literally just plugging this whole thing in, as long as we're careful and use the proper parentheses. And of course, we would expect our pH to not change a lot, but to go down slightly when it does change. Okay. Oops, I think I have too many parentheses there. All right, so 0.5. Oh, I did need that other parentheses. Told you we got to be careful about parentheses when we're stringing the whole thing along. Okay. 0.5 minus, that's not a minus. Okay. divided by another parentheses, 0.5 plus 0.02 and another parentheses. And so now our pH is 4.71.